Okay, great. Let's get started. So, the advantage of being in this time slot is that everybody's already woken up after their lunch. The disadvantage is that I'm standing in between you and drinks over in the exhibitor hall next door. So when I saw the time slot that I got, I intentionally kept my presentation very short. So we're looking at a nice, lean, mean 18 slides. To keep it even more abbreviated, for those of you who are interested to go see something else, I know I was particularly interested in Ken Krugler's talk that's running right now. I'm just going to give you the quick overview so you can get the point in 30 seconds. I'm going to be talking about agile real-time statistics. So this is the intersection of these three different areas that frequently don't come together. And this is being done with two technologies, R and Storm. I'll talk about those, and there's a link to a project here. I'm going to give you a very quick demo on some fun data for those of you who stick around, and talk to you a bit about how it's done. If you want to follow up with me, here's my Twitter handle. That'll be again at the end of the show. All right, so the official topic title is Architecting R into the Storm Application Development Process. This is a collaboration between me at MapR and my colleague Sungwook Yoon. My background, so I'm a principal data scientist at MapR, although I'm not really sure I'm entitled to this title anymore since I neither live in the Bay Area nor am I a statistician. I've been using Hadoop for quite a while, though, since it was part of the Nutch project, which, as you know, is a web crawler where Hadoop came from. I've also been authoring R for quite a long time as well. Since my background is from human genetics, I have a PhD from UCLA School of Medicine, and so R is actually coming from the biostatistics community. So I've been using it for doing some microarray and DNA sequence analysis type of applications for a long time. In particular, working with R and integrating it into with other technologies. So this is right along that same vein today. Sungwook, he has a background in Spark and also in internet security, and he has a PhD in computer engineering from Purdue. MapR, if you're not familiar, we make a big data platform that also ships as part of a Hadoop distribution, and it adds some major technical innovations on top of underneath the interfaces that are part of HDFS and Hadoop MapReduce that add some extra robust stuff and make it perform really well. Okay, so getting into what's Storm and what's R. Storm is what they call a complex event processing system. And what it does is it streams data into a topology. And the topology looks something kind of like this, this art installation here, where you have imagine there's some data flowing into the network at that node at the top, or any of these source nodes pointing down. So that one, this one over here on the right. And let's say your exit nodes would be these two on the bottom here. There's some way that you can flow the data from the nodes on the top through this complex topology down to the bottom and execute some logic on the data as it flows through the system. So Storm is doing something shaped like this. It's very similar to, if you're familiar with Unix pipes and the T command, it's very similar to that, but on steroids. It runs on a cluster in a distributed environment. It's fault tolerant and has some nice characteristics. It can scale out and process millions of events per second, I think is what it says on their website. I didn't run it at that scale. It's used for real-time analytics and machine learning. These are the main applications where you would use Storm, and Oscar Boykin talked about that earlier today. R is a statistical programming environment or programming language, and it's used mostly, at least historically, mostly by statisticians for publishing or who are working in the physical sciences. It's not designed really to be scaled out horizontally. It's intended, or it was originally designed to be used in a desktop exploratory analytics environment, which is why it's particularly a good tool for prototyping very quickly and for visualization. It has fantastic plotting capabilities for supporting this kind of exploratory analysis. But it doesn't scale out very well. Okay, so the question then is, how can we combine these and get the best of both worlds? So one way you might think about doing it would be to have R on the outside and have Storm on the inside. So the user would be, in this case, calling down to an R function that calls down to some kind of Storm function that passes the data back to R and then back to the user for interpretation. This is not an especially suitable approach because for the reason that if you're going to be using R to do some exploratory analysis or model building, you're typically going to want to be doing that on a static static set of data so that you can revise your model, iterate on the model, and understand what you're doing without having the floor ripped out from under you of the changing data. Interestingly, though, you can do something like this if you're going to be using R and Hadoop. Those pair pretty well. And the difference there is that the reference data can be static. So in particular, if you're going to do this on top of MapR's platform, you could, for instance, take a snapshot of data and hand that off to your model building team to be analyzing it, and then when they're ready, they could ship a model back into production. There are a couple of projects that implement this sort of thing of calling from R into Hadoop, one of them being Repay from Purdue, and one called R Hadoop from Revolution Analytics, which is a vendor in the room next door. Okay, but I'm going to be talking about something that looks more like this, where you've got the user calling down to Storm, or the application, I guess I should say, and then Storm down into R, and then passed back up. The reason that you'd rather implement using this kind of pattern is that it enables a separation of concerns. So Storm, you typically see this being used in more of an operational context, where there's a cluster that's running in, let's say, a lights-out data center. And it's doing some processing on data and feeding it into applications more on the back end, or maybe just logging what's happening. And then the R logic would be doing some fancy processing inside. So by separating these things out like this, it enables us to manage ops on its own schedule and manage version control and data modeling on their own schedule and integrate them as needed. It also enables more compact code. So if you were to try to implement some kind of predictive analytics or online machine learning inside of a Storm topology, it could be much more complex and take a lot longer to implement it. So let's consider, for example, I don't have any slides visualizing this, but if we were to try to do a standard matrix normalization routine called a TF-IDF, where you would want to scan across the matrix where you're going to look at all columns and summarize down into some column summaries. We'll put that here. And then we want to take the same matrix and scan across all rows and do some row summaries and put that here. And then take these two things and apply all of it to the same matrix again to transform the matrix into a form that's more usable for downstream applications. That would require many steps potentially and cause it to look something like this in your Storm topology. Whereas if you're using an environment like R that's designed for doing these sort of operations, you could reduce it down to just one step, where you could do your TF-IDF plus a bunch of other statistical stuff and write out some reports at the same time and not have to worry about building a very complex topology to do this. So it's a suitable technology for that. It also allows the DevOps people to be working in software engineering specific tools that R would be not good for at all. Okay, so I realize I'm at Hadoop Summit here, and I'm not sure how many statisticians there are, or even data scientists, but who really likes statistics? The answer, of course, is baseball fans. Even more so, more than baseball fans, baseball team managers especially like statistics. And for those of you who are following how teams are managed in professional sports, managing a team of players is very similar to the way a financial analyst would manage a portfolio. And so just to make sure I hit all the audiences in the room at the same time, if you're not a statistician or a data scientist, maybe you're a baseball fan, and I'm going to talk a bit about the Oakland A's today. In particular, I'm going to be talking about some fresh local data that's coming up. So in about, I guess that's about an hour and a half, there's an A's game versus the Yankees. This is some real-time data. And in particular for this demo I'm going to be showing you, though, I'm going to be looking at an older vintage data set from the Oakland A's, and that is the Moneyball data set. So there was a season in 2002 where the Oakland A's had held a league-specific winning record of 20 consecutive wins, and they still hold this. And also, I like to call out movies in my presentation since I'm from Los Angeles, so let's go Dodgers. Hey you. I thought I'd get some boost from the Yankees fans. We could do a wave for like the Oakland A's, right? Giant. I'm not gonna go, this is dangerous territory. Okay, so if you also don't like baseball, we've got Brad Pitt, so you can write home about that. Okay, so given this, Moneyball was the name of that season where they had this winning streak, and that was the name of that movie, and I'm not going to give you the spoiler of how inaccurate it was as I was researching this talk. But we're interested in detecting the winning streak that occurred during the 2002 season for the Oakland A's. And in order to do this, we're going to use a particular method from statistics called change point detection. And change point detection, what it does is, this is just some data to illustrate on the far right here, and the left I'm describing it. So the point of this type of method is to look at a time series of data and identify where the likely breakpoints are in that series of data where it appears that something occurred. There was a discontinuity of some kind or a change point. Okay? There are two different R packages that implement this, at least. Actually, there are many, many of them, because again, this is R is a language and an environment for publishing advanced statistics libraries. So many different, even exotic methods for doing change point detection are there. But I grabbed two of the more common ones. The first one I'm referencing here is the change point package. Great name. It's more sensitive at detecting breakpoints and has more flexibility as a package. The problem, though, is it's not designed to be used on streaming data. It expects that you have all of the data available at once. You've given it to the algorithm as a chunk, as the time series, and then it will do some forward-backward searching on that data set to identify where the best change points are. There's another package called BCP. This is a Bayesian change point package, and it's actually designed to be executed in an online fashion where it's not assuming that it has all the data visible and the data are streaming into the Bayesian change point package. So if you look at this chart on the right, what I'm showing on the top is the original signal. I'm not even sure what this is a measurement of, but it would be time on the x-axis and some units on the y-axis. And then on the bottom, what you can see is that where your eye is picking up the discontinuity in the blue, in the blues time series, we're showing that there's a, I don't know what the units of the score are, but it's picking up and rendering as a peak that there's likely a change point that occurred at each of those points in the time series. So the architecture for doing this storm calling into R thing that I was talking about earlier in the presentation is to take this Oakland A's data set, and I'm going to accelerated playback for you. I'm not going to stand up here for a full baseball season. Take those data as a storm tap, they call it, stream it into a storm bolt. This is just the name for one of these, again, one of these components in the storm topology. And from that storm bolt, we're going to call down into R. And the R is going to execute this R online change point detector code, okay? Once it passes through there, it's going to output down to another storm bolt whatever it detected. So it may say, oh, I didn't detect any change points, or oh, I think there's these ones exceeded your threshold according to what your R code said, and it will hand those off to the downstream consumer, which is this storm bolt that's writing to Jetty. And in this case, what it does is it posts those data to a Jetty web server that we're using to do some rendering. That's using D3JS, and then we're sitting at the far end of the pipe there observing the data as they're streaming in. This code is all available in my GitHub account, so feel free to pull it down. And I'm actually going to ask you to do that for the data modelers in the room in a moment, and it'll be clear why. Now, for the purposes of this talk, actually what I did is I bailed out here, and I'm not going to show you a live D3 demo because I want to stay inside of slideware mode. So what I did here is I took advantage of one of the nice features of the MapR file system, and I'm writing from R directly out as a series of GIFs, and I'm going to make an animated GIF for you. This is particularly nice that I can do this because R isn't HDFS enabled. It just expects to work with a regular POSIX style file system. So we're leveraging the NFS capability of MapR here to just write from R directly out to the file system. All right. Here's the demo. And this will repeat, and I'm going to walk you through from left to right what each of these things is. So on the far left, what I'm showing you is a 50-game window, sliding window, of data as they're flowing into the online change point detector, okay? And it's showing you on the upper half its best guess as to what the mean value is being displayed. and I'll get into what the mean value is an indicator of in a moment. On the bottom, it's showing you the probability that a change point occurred at any given point in that window. Okay, on the far right, what you've got is that's the most complex one. It's actually the raw data. So the white line is indicating the delta between the Oakland A's and their opponent team, okay? So if it's above 0, that means they won, and if it's below 0, it means the Oakland A's lost. And that's indicated as this cyan line here on the far right, this squiggle. Yellow is the beginning and the end of the 2002 season. That cyan window of vertical bars you're seeing on the far right of the far right plot is the winning streak. And you can see there that the squiggle is mostly above 0 at that point because it's a 20-game streak. Each of the red points is showing you where the change point predictor thinks there might be a change point. And the plot in the middle is a cumulative history similar to what I'm showing you on the far right that is just showing you where the change points were over time. We're basically capturing everything coming from the window predictor, and I'm plotting it for you so you can see cumulatively what's happening over time. It looks like, for some reason, this display didn't loop it, so I'll just back up and run it for you again. So now you know what is going on. Window, cumulative, window, predicted values, and real data, raw data. And so you can see it'll predict things not only at the edge of the window, but they'll kind of sometimes appear back a little bit because there might be some forward context that we needed in order to figure out whether a change point occurred at that point in the window. I didn't get deep enough into the history of the Oakland A's to understand what that winning spike and this depressed period in the beginning of the season are. If you're a baseball fan and would like to share that with me later on, I'd be certainly curious to know. There's some interesting structure in the data set. Okay, and so the winning streaks toward the end of the season, and yellow bar, that's the end of the season. Okay, so some more details about how this is done exactly. It's using a package that I authored and published. It's called Storm. It's published on CRAN. This is the public code repo for R, CRAN, sometimes you'll pronounce it. And it's called Storm or RStorm on my GitHub repo. What it's really doing is it's just enabling you to write this R component that sits down inside of the Storm bolt, and it's managing the communication between the two of those. It's using, to get really technical, the Storm has an interlanguage binding that serializes and deserializes through JSON. So we're communicating to an internal R process in JSON. The nice thing about doing it this way versus some of the other libraries that are available for, there's one other one for integrating Storm and R, is that we maintain a persistent R process that's communicating via the standard in, standard out file handle, which is nice because you don't pay the overhead of re-invoking R for every tuple that you want to pass in for Storm, but it also enables you to do something like a dynamic programming technique. If, as you're processing the data, you want to keep some kind of global lookup table inside that local Storm bolt, you can do that as well, which would be like keeping a running tally, for example. And then you can pass that, of course, down to 0 or more downstream consumers implemented in Java, Python, whatever, which ultimately goes out of Storm context. That's the general model. It's really easy to implement. Here's what it looks like. In R, you basically just declare this object, and you implement a Lambda function. Lambda function takes a data tuple, processes it, and maybe modifies it, and emits the data tuple. On the Storm side, you're extending this thing called shellbolt, and all you really need to do is write a constructor that calls out to the path of where it can expect to find your R script, and you can implement it. So that's really all there is to it. I should comment here also that this particular design supports the Lambda architecture, which you might have heard about before in the conference or even before that, because we can essentially treat this process here in the Storm bolt. Again, if we're not doing dynamic programming and doing all state inside the Lambda, this is really a one in, one out kind of operation. Process one at a time. So you can certainly treat this R Lambda function as a monad and plug it directly into a Lambda architecture design. All right, so as far as the results go, I kind of glossed this on my animation. I actually didn't pick up the change point, okay? I couldn't figure out where the beginning of the game was, or the beginning of the winning streak. but at least not using the score difference. So I was just using Oakland A's minus the score of the other team to try to detect it. But by all means, if you think you might be able to see this thing by looking at something more sophisticated like the variance or I don't know what, I'm not a statistician, please let me know and we can merge your chain. Send me a pull request on GitHub and I'll be happy to merge your code in. You can take a look at the R code that's there. This particular type of application, I was trying to decide what I should show you that would be interesting for some real-time data processing. I thought about looking at Twitter data, but sentiment analysis has just been totally overplayed. And this, at least in a conference context, this is particularly interesting though for some customers that I run into in my consulting capacity at MapR. In particular, we can use this sort of thing, or similar systems that perform similar functions to this are being used in fraud detection and intrusion detection scenarios. Also in marketing, for doing marketing applications of trying to understand the signals coming from an individual and whether they're likely to buy, so like a propensity to buy calculation, either on inbound, outbound marketing, or social media stream analysis. Really, it's generally very general purpose. I've also run into a use case of this sort of thing in a customer support scenario where there would be a call center and an agent might be speaking to a customer, so you have a dialogue between the two of them, and you might be trying to detect where a call has gone south, and maybe you should escalate the call up to the next level of support, sensing the customer is becoming frustrated, or the use case I saw, they were particularly interested in words like manager or lawyer, so if you want to get escalated in support, you can try using those keywords on your next call to a call center, et cetera. You can imagine many things you can do on time series like this. And that's it. That's the end of my presentation. So I'll take questions now, and I also want to point out that that lower right link, that's my username on SlideShare. So if you want to grab these slides, slideshare.net/AlanDay, it's all already posted. Questions? Okay, yeah, please come to the mic.
When I was thinking the injecting R function from Storm is Java-based code, right?
Yes.
What kind of challenges did you see, or the implementation you have? Can other user take the similar implementation to implement?
I can barely hear you. Can you speak more?
Can other users take the same implementation that you have done to implement other R functions?
Implement other other Lambda functions, you mean?
Other R Lambda functions.
Yes, of course. So if I just jump back here to the code example, if my thing will work. You basically just need to have one function called Lambda. So I'm assigning a function onto this slot. There's some R syntax here. Storm $lambda. $lambda is a slot on the object. It's like an accessor. You can think about it like that. And I'm assigning it that particular anonymous function, which takes one argument, which is the storm object. That storm object will contain the input inside of it in this tuple field. And then what you're doing is you're just manipulating that tuple field and then emitting the tuple back out. So if you can put everything inside of this function, Lambda, that fulfills your requirement for your application, yes, you can implement whatever you like. Okay, thanks very much.